Okay. So this is the study we are working with. We did the structure last week, during the last week session. We are done with carbon, air quality, agricultural intensification, impact on economic growth, and health investment as a moderator. So this is the structure we are working with. It looks like I didn't save my result. Oh. Recording. Okay, so we did the summary statistics and then we saved our results. We did a correlation analysis. We did slope homogeneity test and then the cross-sectional dependency test. We explained what each result mean. Then we did co-integration. The co-integration, we ran 3 models. We ran the Westerland, we ran cow test, we ran then Pedroni. So we got to unit roots and then the main model estimation. And maybe if time permits, we do heterogeneous analysis and then causality test. Okay. So we are still using the AI integration, learning how to speed up with our result processing and everything with AI, how AI can help us to fasten our result processing, summarizing our result, and then presentation of our findings. Okay. So
Hello, Seth. I'm back now.
please, you can talk.
Can you hear me? So I wanted to ask some question concerning what we did last week. So we ran the Jagbera test, and I wanted to know when you finish running the Jagbera test, what's next? Or what was the decision? What's the essence?
Yes, the descriptive analysis. I said that you present descriptive analysis so that your those who are interpreting the results will factor the descriptive analysis into consideration. So you are telling your readers that the data you used is normal, and you can adopt models that follow normal distribution. If it is not
Okay.
normal to, you can adopt models that does not follow normal distribution. But
Okay.
you are presenting the descriptive so that your readers will know that you are dealing with a data that follows normal distribution or not normal distribution. So it's better you give an overview of your data to the readers. But the JB test is used to test the distribution of the data. Is it normal or is not normal? And if it is normal, it can prompt you to adopt a normal distribution model that follows normal distribution. And if it is not normal to, we have models that deals with that. But most of the advanced econometric models, advanced models, it can cater for both. It can cater, unless maybe you are dealing with a primary data or something, and you need to do some pre-tests, then you factor that. Is that okay?
Yes. Okay. Then with the VIF2, I realized that later when I went to run, there were some that were getting some big figures. When you were doing it, you got it, you did something, but I forgot, I couldn't catch that one.
I didn't do anything. No. The first one I ran, I included the moderating variable in the test to show how when your VIF goes up, it looks like. So like, let me open the data again and show it. So you see, I think this was it. I'm running it again for you to see. Okay, so this was the regression. This regression contains the moderating variable, the interaction term, the interaction that we created. And when you run the VIF, you see that there are 385, 332, which is above 10. And it's not good.
Yes.
It's not good. So, but the perfect one should be like this. So this one does not include the interaction term. So you see this one. This one
Okay.
is okay. So if you run your normal variables and they are high like this, it means there's a problem. You have to change the models. If there's multi-collinearity between two models, two variables, you have to drop one, or you can replace one. So you have to work on it till you get VIMs which are less than 10. Uh-huh. So you have to get a VIF something like this. But if it is 9, 8, 7, it's acceptable. But if it is above 10 like this, then it's problematic. You need to address it before you continue.
Okay. Okay, nice. Then for the Westerland co-integration too, I realized I didn't do it for inflation. I wanted to understand why we didn't do it for
Westerland,
inflation.
I didn't do it for
Co-integration.
inflation.
You didn't add inflation, yeah.
Ah, is it Westerland? The variables you can add to test should not be more than six. What is it? One,
Okay.
two, three, four, five, six. It shouldn't be more than six. If it is more than six, it will not work. That's why I dropped the inflation. Inflation is just a control variable. So our main
Okay.
variables were CO2, PM2.5, nitrous oxide. So that alone is enough. That's why I dropped the
Mm,
inflation. Because if I add it,
okay.
it will not run.
Mm,
Mhm.
okay. Thank you. Thank you.
So let me add it and see. I think the Westerland, if it was giving us, they said that I think I changed our period is not enough. So you see, so let me add the inflation and see. You see, no more than six covariates can be specific. So it's because the
Okay.
variables are more than six. That's why I dropped the inflation.
Okay. Okay.
Okay,
Thank you.
no, what's any question? Yes,
So, uh, uh, so if you have more than like 10 variables, and then for the Westerlands, you can run only six at a time. So if you run the first six, and maybe you want to run the second six, are you supposed to add the dependent variable to run the other ones, or you just continue with those that you didn't run?
you see the Westerland, not even only the Westerland, the co-integration, it does not give you individual results. Hey, it's like I've muted myself when I'm talking. Okay, that's fine. So the co-integration does not give individual result to each variable. It gives a combined result, like what you see here. It has given us a result, whether there's co-integration or not. So it's not like you have to go and run it again and add inflation. Our main focus is between the three. Is between the three, the CO2. So if the CO2, your main variables are inside what you tested, it's okay. But if you have a different dependent variable, sorry, if you have multiple dependent variable, then you have to run each one. If you so maybe if we are having two dependent variable, Then we have to run the first one and also the second one. But in this step, we have only one dependent variable, which is GDP. So if you see the code, you can see that the GDP comes first before our three models. The same thing applies to the cow test and the Pedroni too. It all follows the same process. Mhm. Yes. So you can see that it's okay. So it's not like you have to run and run and run it again. No. Is that okay? Any other question? Any other question? Okay, so um I'm going over, I think beginning, we converted our data to log. We encoded the country to create a country ID. I said we have to change the alphabetic values, which is the string, to numeric values. So we generated a country ID or the country identifier. Then we set our panel structure. I said in STATA, you have to set it. If it is a time series, you have to set it. If it is a panel, you have to set it. So that STATA will know the kind of data you are dealing with. Then we did our summary statistics. The summary statistics, I said we have the detailed one and then the summarized one. This is the detailed one. It gives you the observation, mean, standard deviation, minimum values, and then the maximum values. And the details also give you more details into the summary. It gives you the skewness, ketosis, variance, largest values, and then smallest values, and even including percentiles. And then we did the JB test, which is the Jagbera test. It's used to test for normality. Yeah, so we did it. Then we generated our interaction term. Because we said we are doing moderating analysis, and we said that for moderation analysis, you have to multiply the moderator by the independent variables to create an interaction terms or interaction variables. And we did that. We generated those variables too. And then we did correlation metrics. So the correlation too, we did one without the interaction variables, and also we did one with the interaction variables. And then we did pairwise correlation. I said that the pairwise correlation comes with significance values like this. If you run it, it comes with significance. It comes with significance. It tests for whether the relationship is significant or not. And then we did VIF tests. And we said that the VIF is used to test for multicollinearity among the variables. And we said that if it is above 10, you need to address it. Like this one, we're having a high values because of the interactions I added. So without the interaction, we had a perfect collinearity, a good collinearity. We don't have any issue with collinearity. And then looking at our work, I showed how you can easily use AI to create a table and present your work nicely. So you can see that I have the summary statistics, I have the correlation, and the correlation, you can add the VIF under it. So you see that CO2 have VIF of 1.8, PM 2.5. So each of the tests or each of the variable have its correlation values and then VIF under it. And also we have the slope homogeneity test. The slope homogeneity test. We found 0.00. We explained how to interpret the homogeneity. We learned how to interpret the homogeneity if it is significant based on the null hypothesis. Based on the null hypothesis, we tested, where was it? Okay, so this was the null hypothesis says the slope coefficients are homogeneous. Slope coefficients are homogeneous. And if it is significant, we reject the null hypothesis saying that the slope coefficients are heterogeneous. We also interpreted what it means to have heterogeneous slope. Okay. And then we did cross-sectional dependency. We did cross-sectional dependency test. That one too, we used I said we have a lot of tests. E-views have some STATA and even R, Python, and all others. And the STATA one we were using was Perseran 2015. Perseran 2015. We use it to test for our cross-sectional dependency. We have the Perseran 2015, Geodis RIS 2021, CDW with power enhancement from Faneta, and then Perseran and Shear with 4 pieces. That one too is here. We also stated that we explained the null hypothesis and then how to interpret the null hypothesis with the results. Then we did the co-integration. We ran Westerland, but because of our period or the number of period we're working with, we're having problem with Westerland results. So we chose cow test and then Pedroni. And this was the result that we had. This was the result that we had. So yes. So that one too, we interpreted it based on the null hypothesis. The null hypothesis and what it means. What it means. Okay. So we skipped unit root, so we said we will come back to it. Any question before I start today's session? Any question? Okay. So I think there's no question, so we can continue. So we are at unit root. Unit root, we have first generation unit root, and then second generation unit root. The second generation is used when you want to, the second generation is used when you want to account for cross-sectional dependency. The first generation is the normal unit root. It does not account for cross-sectional dependency. But the second generation accounts for cross-sectional dependency. So what you can do is you can always run your unit root test first. When you run your unit root, and then, sorry, you can run your cross-sectional dependency test first. If you run your cross-sectional dependency and you find that there is a cross-sectional dependency present in your data, then you use the second generation. But if you run and there's no cross-sectional problem, then you can use the first generation. So the first generation do not account for cross-sectional dependence, but the second generation test account for cross-sectional dependency. Okay, so the first generation test, we have the Levin-Lenchu test, which is the LLC. We have the IPS, which is in Perserantian test. And then we have the Fisher type test, which is ADF, Fisher, and PPP. So we have the ADF and then the Filiperon. And then we have the Harris-Tavares test. They are all first generation unit root tests. Okay. And then the second generation, which accounts for cross-sectional dependency, we have the SIFs. So the Fs is the first generation, and then the SIFs is second generation. Please, can you hear me? I think someone is saying there are echoes coming from my back. Please, is it the same for everybody?
Yes, so.
Okay, I think someone muted, unmuted himself. Okay. Is it okay now?
Yeah, it's okay.
Okay, so I think someone unmuted himself. That's why. Okay, so let's continue. Let's continue. So we have the second. So the reason why we have the second generation at the top is because our work, we found the presence of co-integration in our, we have presence of cross-sectional dependency in our results. So we have to use the second generation unit root test, which is the SEPS and then the CADF. CADF. So you have to use the SEPS and then the CADF, which is the second generation. And then the first generation, if we didn't have a cross-sectional problem, then we can use the first generation test. And the unit root tool, you have to test at levels and then at first difference. You have to test at level and also at first difference. Some people test for second difference, but if you test at level,
He was talking about
who has unmuted himself? Do you have a question? If not, then please kindly mute yourself. If you join, then you mute yourself. Okay. So when you test at level and it is still not stationary, then you can do first difference to see if it is stationary. It is not that prudent to do first test and also second test. Do second difference, third difference. No, mostly you should get stationarity at first difference. If not, then you have to look at your data again. Okay. I'm trying to open the AI where we left off the last time. Okay. So let's run the second generation at levels. The model I'm using the SEPs at max lax 4 and then the BG lax 4. You can change it provided you can justify why you selected that lag. And it should always back by a study or an empirical study. So from what I normally used, I used maximum lag selection of 4 for both the max lags and then the BG lags. You can change it to suit what you want. So let's run for GDP, for CO2, PM2.5, nitrox, health. Please, if you don't have the SIPs, kindly install it. If you don't have the SIPs, kindly install it. You can use the SSC install XT. If you still don't have this data, after the lecture, you can DM me. I will send it to you for you to install. Same thing applies to Smart PLS and eViews. So the command is XT then you select the variable, then you do your mark selection for it. So these are our critical values. The Perseron panel unit root test with cross-sectional and phase difference mean included for GDP. Determines choosing constant. Determine lag selection criteria decision general to particular based on F-joint test. So the null hypothesis is homogeneous non-stationarity. It means the null hypothesis states that it is non-stationary. It is non-stationary. That's the null hypothesis. But in SIPS or unit root testing, we use the SIPS value to compare the critical values. You can run all and then interpret your results. We compare the SIPS value, which is the negative 2.135. Please hope you can see my AI screen.
Yeah.
Okay. So we compare the SIPS value to the critical values. So you can present it like this. You check whether the SIPS statistic or the statistic is less or greater than the critical value at 1%, 5%, and 10%. Mostly we use the absolute of the SIPS, which is 2.135. And then the null hypothesis is homogeneous non-stationary. Interpreting this is a bit technical, so please kindly follow me. You use the SIPS, which is 2.135, to compare the critical values. So here we have 2.14, 2.25, 2.35. You realize that this one is less than all of the critical values. The SIPS, the absolute SIPS, is less than all the critical values. Please hope you can see that. The SIPS value is 2.13, and then the critical values are 2.14, 2.25, 2.45. So the SIPS statistic is less than the 5%. So let's focus on the 5% since that's what we are using for it. So if this SIPS statistic is less than the critical value, it means it is not significant. If it is not significant, it means the presence is not stationary. Let me go over again. I know it's a bit technical, but let me go over again. Here, it is not p-values. It is the statistic and then the critical values. Take the absolute of the statistic and the absolute of the critical values. When I say take the absolute, it means forget the negatives before it and take the absolute values. If you take the absolute values, the SIPS statistic is less than the 2.13 is less than 2.25. If it is less than the critical value, it means it's not significant. And we learned from our previous session that if it is not significant, we fail to reject the null hypothesis. If it is significant, we reject the null hypothesis. Like what we did here. The co-integration, we did the p-value, and then the null hypothesis says that no co-integration. And we said that if the p-value is less than 0.05, it means it's significant. And if it is significant, we reject the null hypothesis. If it is not significant, then we fail to reject the null hypothesis. The same thing applies to the unit root. Here we use the statistic, the safe statistic, which is this one, to compare with the critical values. And the null hypothesis states that it is homogeneous, non-stationary. And I'm saying that if the statistic is less than if it is less than the critical values, then it is not significant. If it is greater, if the safe statistic is greater than the critical values, then it is significant. So it's like an opposite of the p-values. So here, the safe statistic is less than the 5%. So if it is less than the 5%, then it is not significant. If it is not significant, we fail to reject the null hypothesis. In other words, we accept the null hypothesis. And what is the null hypothesis? The null hypothesis is non-stationary. That means the variable is non-stationary. Please, do we understand? Any question?
Hello, Seth.
Yes, please.
So the lags you chose for, what informed your decision to choose for?
I I use 4 lags based on empirical studies, like I said earlier.
So all of us can also use for, right?
Provided you can get an empirical study to back it. Or you can do, how do we call it? We have lag selection test using the archaic method, and then we have methods to do lag selection. Using the AIC method, and then we have other methods to do it. You can run that one to get your maximum lags, or you can get an empirical literature to back your lag selection. But for me, have you been using 4? Then I will cite a study that I use 4, and I'm good to go.
Okay, then we will all use for.
No, you can read to expand your knowledge so that you will not be limited to what you are learning here.
Okay.
Yes, I have to know how to apply the lags. So you can go and learn at what point that you can use 3, you can use 2, you can use 1, you can use, so that you expand your scope. Do not be limited about only this one. Yes. Okay, thank you. Any other question? Okay, so let's run the remaining ones and see. So it means that, and please, we are doing at levels because we have not find any difference. So we are doing for at levels. Okay, so let's run for CO2. Think I have to call some people to help us interpret it. Okay, who will help us interpret the CO2?
Let me try.
Let me try and see.
Okay.
Okay, so the set statistics bigger than all the critical values. So we reject the null hypothesis. So this one is stationary.
So this is stationary from Teria. Teria is saying that since the saves is greater than the absolute saves is greater than the critical values, then it's stationary. Let's interpret it and see if, okay. So we can see that it's the same thing. It's the same thing. So the saves value, please use absolute. Use absolute. Forget the negative before it and use absolute. So you realize that the CO2 2.53 is greater than 2.14, and the 5% 2.25. That means the variable is stationary at level. Stationary at level. Okay. So let's run for the PM 2.5. Alote, interpret this one for us. Today they are on you. Is this one significant, or is it stationary or not stationary?
This one is not stationary
Why?
because the SIP value is less than the critical value.
Okay. So what does it mean in terms of hypothesis testing?
It feels, you see, it feels to accept the null hypothesis right now.
So if we fail to accept the null hypothesis, so what does
It's
it
not
mean?
significant.
That
Not
means it's not
significant.
significant. That means it is not non-stationary. It is non-stationary. Last variable. Someone should interpret this one for us. The nitrous oxide. What does this mean? You can unmute yourself and interpret it for us. This is the unit root test for the nitrous oxide. Someone should unmute and interpret it for us.
So what it
This is
means,
stationary.
Please, who was talking? You can talk.
So therefore, we fail to accept the null hypothesis.
Okay. That means it is stationary. Okay. So let's run for the remaining one and let's summarize the results. So that's how you run for all the variables. So, and that's how you interpret it. So that's
Then I have a question. So is so far the ones we've run. So far the ones we've run, what we see is that it seems the SIP's value is either greater than all the critical values or it is less than all the critical values. So would there be an instance where the SIP's value will be greater than some and then less than some? And in that instances, what do you do?
yes, it's possible. It's possible that it can be greater than 10% and less than 5%. Or that's why always you have to make a decision from the beginning, the significance value you are working with. And I said from the beginning that for social sciences, we mostly use 5%. So 5% is what in social sciences is the medical field that mostly use the 1%. But social sciences, we mostly use 5%. So if you are using 5%, then you use the 5% to make decision. So if you are having mixed critical values, You can base your result on the significance level or the critical value you are working with. But if your study is in social sciences like economics, sociology, those fields, then you have to use the 5% threshold. Yeah. But for medical fields, you can use the 1%. Okay.
Seth, you are muted. I don't know if you are talking.
I've talked for like 5 minutes. Thank you, Tavia. Thank you. So I was saying that for the first difference or for the difference unit root testing, you can generate the difference variable using the gen d dot the variable. Then you create those variables before you find the unit root on the generated variables. Or you can use this simple method by using the d dot the variable like this one. So you can see that the first difference, you have d dot in front, d dot in front, d dot. And please, if you do at level and all the variables are stationary, there's no need to do the first difference. But if you test at levels and you're having a mixed stationarity, which is some are having which some are stationary and some are not, then you have to do the first difference test. If not, if you have all of them stationary at level, then there's no need to do the first difference. But in our case, we had some to be stationary and some to be non-stationary. And it's difficult in econometrics to have all your variables stationary. Yes, it's difficult to have that, but it's not impossible. It's possible. Just that it's rare. So you can use this to test. Okay. So what does this mean? The first difference, GDP, someone should interpret this one for us. What does this mean? Someone should interpret this result for us. Is it
It's
stationary or not?
stationary.
Why?
Stationary.
Why are you saying it's stationary?
Because the safe statistic is greater than all the significant values.
Great, great, great. So we can see that at level, that variable was not significant. But when we did the first difference, it becomes stationary. So for the at level, the safe statistic was less than the critical value. So it was non-stationary. Then we run the first difference, and then now the safe value is greater than the critical values. That means it is now stationary. It is now stationary. So we run for all of them. So you see that this one too, the safe value is greater. That means it is significant. So let's run for all of them. So let me get the results. So let me run at levels again for all of the variables. And then I will run for, because I want to get the result for AI to summarize it in a table for me. So now I've run both at level and at first difference. Let me copy all the results for AI to summarize so that we will understand it proper. If you are running alongside me, you can also follow the process I'm using. If you also want to extract it manually, that one too is fine. But I don't have time to do that. Okay, so let's see the results. So you can see that the first one, the GDP was not stationary at level, but after first difference, it becomes stationary. That means it is I1. When you say I1, it means integration order. Integration order. So it is integration order 1. If you have unit root or stationarity at level, it is integration order 0. If you have stationarity at first difference, it is integrating order 1. If it is second difference, it is order 2. So this is how we present the unit root results. So CO2, when we ran it, we realized that at level it was stationary. So definitely at first difference, it will still be stationary. So it is integration order 0. Always try to show the order, the I order is good for interpretation. Then PM 2.5 was non-stationary at first at level, then it became stationary at first difference. Sorry, it became stationary at first difference. Nitrous oxide was both stationary at level, that which is I0. So you can see that we have a mixed order. We have a mixed order. This is what we call the mixed order, and it influences the choice of model. It influences the choice of, we have a model which you can use for only I0s. We have a model that works with only I1s, and we have a model which works with a mixed order. So it's not just you are not doing anything anyhow. It influences the choice of model. So you have to check models that works with mixed order. Okay, so let's do for the other model, which is the CADF. The CADF. So that was the first one we did is the CIPS, which is cross-sectionally augmented impersonation. So the impersonation is a first generation model. It's here, but the CIPS is the cross-sectional augmented form of the second one or of the first generation model. The cross-sectionally augmented it accounts for cross-sectional dependency. So let's look at the CADF, which is the covariate augmented Dickey-Fuller test. The covariate augmented Dickey-Fuller test. That one too is a model used to test for, it's a second generation. So always try to test like 2. Try to test like 2 unit roots to make your result more stable and reliable. So you can install the PERS CADF. PERS CADF. You can install that. The PERS is Perseran. So Perseran CADF. That one too, I'm using lag 1. I'm using lag 1. And as I said, all my lag selection is based on empirical literature. You can also do that. So the CADF, sorry, the SIPs use the max lag and then the background lag. So we have two max selection. You have the maximum lags and then the background lags. But the CADF have only lags. It's not specific like max or background. So but mostly it is the maximum selection or maximum lag. So I'm using a lag of 1. And mostly to this lag is influenced by your period of analysis. Your period. So you see that when I was running the Westerland, when I used one, I think where's the Westerland? Yes. When I used 1, it says that my period is not enough because the lag means that the data will go back. The data will go back. So you have to make sure that your period is enough to run that. So you see that I'm using lag of 3 and it is not working because my observation is 24. When it takes, my observation is 25. When it takes a lag of 3, it remains 22. And the Westerland requires at least 24 observation to run. So always check your data period too. So Teria, the data period also influences the lag selection. Yes. So the CADF is also another model. If you don't have it, you can install it using the SSC install. Then let me run it. Okay, so this is the CADF. Yes. It says the Perseverance CADF test for GDP, cross-sectionally average in first period extracted and extreme t-values truncated determines deterministic chosen constant t-bar tests augmented by lag 1. Yes, we used lag 1. So we have the t-bar here. We have our critical values here, the 10, 5, and then the z t-bar, and then the p-values. So let's look at how it will be interpreted. Then the subsequent one, we interpret them. So this one too uses the same critical values. Using the t-bar, and then we have the z-bar, and then the p-value. Let's look at how the decision is made. The t-bar statistic, you see the SIPs use the SIPs statistic, but the CADF uses the T statistic or the T-bar statistics. And in our result, the T-bar was 1.97. It says that 1.97 is less than all the critical values, and p-value is well above 0.1. This means that we fail to reject. So it means we can even base on this decision on the p-values. But let's try to compare the T-bar and see. The T-bar is 1.971, and then the critical values are 2.140, and then the 2.250, 2.450. So the T-bar is less than all the critical values. It's less than, so you can base it on only the 5%. That means it is not significant. And even if you look at the p-values, so even the CADF make it a bit less easy for us because it give us p-values. It give us p-value, which is we had 0.211. That means it is not significant. If it is not significant, then we reject. So if it is not significant, then we fail to reject the null hypothesis. We fail to reject the null hypothesis. And the null hypothesis states that it is non-stationary. Non-stationary. That's the null hypothesis. So it's the same as, it follows the same process as the SIPs, which is non-stationary hypothesis. Okay. So you can just, so this one is easy. You can just use the p-value to determine it, to determine the result. If the p-value is not significant, that means it is not significant. You fail to reject the null hypothesis, and the null hypothesis is not significant. So if you are failing to reject the null hypothesis, in other words, we are accepting or we are taking the null hypothesis, which is non-stationary. Or you can also use the same process that we used under the SIPs to use the T-bar or the T-bar statistics to compare with the critical values, and realize that the T-bar is less than the critical values. I said take the absolute. It is less than the 5%. Therefore, it is not significant. It is not significant. So we fail to reject the null hypothesis and assume that it is non-stationary. So GDP is non-stationary at level. For CO2, someone should interpret the CO2 for us. Prince Nyako, can you interpret the result for the CO2 for us? Prince Nyako, Collins, are you there?
Hello.
Oh, someone should, I want to see whether you understand what we are doing.
Yeah, yeah. So the CO2 is stationary
Why?
because I use the p-value. The p-value is less than 0.05.
Okay, so if it is less than 0.05, what does it mean?
It means that it is stationary.
Okay, it means we reject the null hypothesis, and the null hypothesis
Hypothesis,
is
yes.
not stationary. So if you are rejecting the null hypothesis, it means it is stationary. It is stationary. And you realize that the T bar is also above or greater than the critical value at 5%. Yes. So the question someone asked, you see that the critical value at 1% is greater than the T statistic. Is greater than the T statistic. So if you go by the critical value at 1%, you will say that it is not stationary. But we are using the 5%. As I said, the 5% is our threshold. And also the p-value also supports the rejection of the null hypothesis to stationarity. But if you are using the 1%, then you can say that it is non-stationary. But we are using 5% critical value. 5% critical value. Okay. So let's run for all the other results. So that one too. We have the result here. Who will interpret the last one for us? I want to know if we understand all that we are doing. Who interpret the inflation, the unit root for the inflation for us? Please, someone should interpret it for us, a volunteer.
Okay, so again, using the p-value, the with inflation, we reject the null hypothesis. So it is stationary.
Okay, great. It is stationary. Using the p-value, you can see that it is significant. It is less than 0.05. Then you reject the null hypothesis to say that it is stationary. So that's the at level 4. or the variable? So you can do the same. You have to run for at first difference, to also, you just put the d dots at before the variable. So let me make AI summarize the unit root results so that we can incorporate it into our work. If you have a question on the unit root, you can ask. We are done with the unit root. If you have a question, you can ask while I'm trying to summarize the results into a table. Oh, okay. So I think now we have done all our pre-testing or the diagnostic tests or the pre-estimate model selection testing. So we can, okay, so let me copy the table and insert it into our, when we are done, I will give the work to someone to go and write it as a full paper for us to publish. So you can present your results or you can combine all the results into one. Okay. I'll combine everything into one table when we are done. But for now, let me leave it like this. Okay. Please, any question? So now, if you get to this point, you select a model for your study. You select a model, and the model will be based on all the tests that we have done. All the tests that we have done. We have done slope homogeneity test, cross-sectional dependency test, co-integration test, and then unit root test. And we said that the slope homogeneity tests the difference in the coefficient of the individual countries, the differences between the countries, the differences in the countries. And we realized that it is significant. That means there is differences or it is heterogeneous. The slope is heterogeneous. They are different. And then the cross-sectional is also used to test the dependency of the countries. It means each country depends on the other. If something happens in the one country, it affects the other countries. That's why all of them show significance. That means there's a presence of cross-sectional dependency. And then we also did the co-integration, which is used to test the long run and the short run relationship between the variable. And we realized that there is a co-integration. That means there is both long run and then short run. So we have to use a model that accounts for both long run and short run. And then we did unit root test. And then the unit root test, we have mixed relationship, mixed order. So we have I0s and I1s, I0, I1, I0, I1. So this is a mixed order, So all these influences the choice of model. So you can't just choose any basic model to run. You have to use a model that accounts for all this. A model that accounts for both slope homogeneity, cross-sectional dependency, co-integration, and then the mixed order. So that means based on our results, you have to go for an advanced model, a model like GMM, AMG, PMG, CCEMG, and maybe cross-sectional ARDL, cross-sectional ARDL, cross-sectional ARDL. So we will run the best models that I will recommend for this type of results will be either the PMG, pooled mean group, the common correlated estimates mean group, and then maybe GMM is also good for this result. Two-stage least square is also good. Disco-Cray is acceptable. It's acceptable, but it does not address all the above problems enough, especially the cross-sectional dependency. But it is acceptable, provided you can give reasons. And then the GMM is accepted. So let's see some of the models that we have. So please, now from here, we have to estimate our main models. And I will try to estimate a lot of models. Today, we will not treat quantile regression. Quantile regression will be a full lecture on its own. GMM will be a full lecture on its own. So let's see this Cochrane. Let's see. We have the mean group, common correlated effects, this Cochrane, PCSE. Some of the models it should be a full lecture on its own, so we will not treat them today when we get there, because it's a full work on its own. So let me line up the models that we will be treating today and see. Okay, so panel corrected standard error. So these are the models we are going to treat today: the FE, RE, the Cochrane standard error. Please, if you have a question, you can ask while I set up the structure. DKSE. Then we have
Hello,
the...
sir.
Yes, please, you can talk.
So all these models that you've listed here, do they account for all the problems that we've encountered on the road in
Some
this
does, some does not. But due to the nature of this class is a lecture class. It's not, we are not writing a paper now. So I will run most of the models, both that addresses it and those that does not. But I've stated that the ones I will recommend is the CCEMG the pool mean group, and some level of the score create the cross-sectional ARDL. The cross-sectional ARDL is highly recommended because it addresses the cross-sectional nature, and also it estimates both long run and short run because of the co-integration. Pool mean group is also good for cross-sectional dependency test. The random and the fixed effects is the basic form of panel analysis. You cannot go without it. You cannot go without it. So we will estimate both of them. But in this case, based on the kind of result we have generated, it is not appropriate to use them. You can use them as a robustness test. You can use them as robustness tests, but it is not appropriate because it does not address the homogeneity problem. Even the homogeneity, you can use the random effect to cater for it a bit. But because of the cross-sectional dependency problem, the mixed order of unit root, and then the co-integration problems, that means the FE and the RE is limited in this case. It's limited. But this is a lecture. This is a lecture. So I'll run these models for us to interpret them. Yes. We will have time for GMM models. That will be a full lecture. We will run GMM models. And then we will also do quantile regression as a full lecture. And then we will also do the ARDL, CSARDL, VAR, and all other models. We will do all of them in due course. Because those models comes with its own pre-estimate and then the post-estimations. So we will do them later. We will do them later. So, and we have the robustness. And this robustness, I said you can use lag, you can use different or similar DVs, and then the time effect. Okay, so let's go back. So we have the FERE, the score create, and mostly FE and then RE is determined from Houseman test. You have to do Houseman test to determine which one you have to use. But for today's lecture, we will run all of them. We want to know how each of the models works. Then when we take them one by one, we will go deep into each of them. And before you start, you have to run, if you want to do the Houseman test, I think it is here. You can run, you have to run the FE. Let me give space so that I type the models for you to see. You have to set the time, the panel time. You have to set the panel, the ones we set earlier. If you do not work on that, or if you do not run that, your models will not work. So always use the XT. So normal OLS is reg. That's what you use for the VIF. Reg GDP is our dependent variable. So you select your dependent variable, then you select your independent variables. These are our independent variable. So this is our OLS regression, which we said is the basic form of regression. It's not suitable for publication. But when you are running a panel regression, then you put the XT in front of it, the FT in front of it. So XT reg, then you run it. So you see that we have the random effect. So you can put comma here, RE, so that you can specify that you are running a random effect GLS model, random effect. So that's the RE model. So let's try to interpret the result. Our within R square is 59. R square is 59%, which is okay, it's acceptable. R square of 59 is acceptable. And then our chi-test 2 means the model is significant. The model is good. Our model is good. Our model is good. So let's come to the result. I will interpret 1. Then we will look for volunteers to help us interpret the rest. So CO2 have coefficient of 0.25, 0.25488. So 0.25. It has a standard error of 0.025, z-score of 9.92, and then p-value of 0.00, and then a confidence interval. Any model like this, we have 3 ways of deciding whether your variable is significant or not. This thing, if you don't know, and some people go and manipulate their results, and if you don't know, you can manipulate your results and they will catch you. They will catch you. So please learn and don't go and manipulate your result, because all the figures there comes from somewhere. It is the addition of some variables, subtraction of some variables that gives each of the variables there. So CO2 is significant because the p-value is 0.00. You can also interpret the significance or determine the significance based on the z value. The z value. If the z value is more than 2, if it is more than 2, it will be significant. If the z value, some of the models will also show t value or t statistic. Some show z. If it is more than 2, it is significant. If it is less than 2, it will be insignificant. Using the z value or the t statistic. So you can present your result and use the z value to present it. Or you can present your result to use the p value. You see the p value, z value for the CO2 is more than 2. It's more than 2. And the p value is also less than 0.05. And the confidence interval, if your confidence interval crosses 0, it is insignificant. If your confidence interval does not cross 0, it is significant. So if the p-value and the z-value is confusing you, you can rely on the confidence interval. If your confidence interval crosses 0, it is insignificant. If it does not cross 0, it is significant. What do I mean by it crosses 0? What do I mean by it crosses 0? You see that the CO2, the confidence interval starts from 0.20, 0.2045476 to 0.305218. When you are counting from 0.20 to 0.30, there is no 0 in between. When you look at the PM 2.52, the minimum confidence value is negative 0.44 to negative 0.302. Moving from negative to negative, there's no 0. There's no zero in between. There's no zero in between. From negative to negative, there's no zero in between. It means it's significant. That variable is significant. Looking at the nitrous oxide, the first value is 0.01212, 0.106. Both positive at the end. Moving from negative 0.01 to negative 1.06, there's no zero in between. But let's look at the health. Let's look at the health. For the health, the minimum confidence value is negative 0.75. And the highest confidence value is 0.01. Moving from negative value to positive value, you will cross zero. It means that variable is insignificant. So if you cross-check that value with its p-value, the p-value is more than 0.05. And then the z-value is less than 2. It's less than 2. So you can see that that variable is not significant. The same thing applies to the exchange rate. It moves from negative to positive. It moves from negative to positive. It crosses zero. It crosses zero. So it's not significant. It's not significant. And if you look at its corresponding p-value, the p-value is so high. 0.87 is not significant. Z-value, you can see that the z-value is also less than 2. It's also less than 2, which is not significant. Let's look at inflation. So inflation, you realize that the confidence interval is moving from negative to negative, negative to negative, negative to negative. That means it does not crosses zero. So it is significant. So you can present your result with a confidence interval. You can present your result with the p-value. You can present your result with the z-statistic. Now let's interpret the coefficient. Let's interpret the coefficient. Any question?
Hello, Seth.
Yes.
Yes, so the z values, do you take their absolute?
Yes, absolute.
Okay.
Absolute, yeah, absolute. Thank you. Any other question? Okay, so if there's no question, then let's
Can I ask a question?
yes, please, you can.
Please, what the confidence interval is always 95.
Please come again.
The confidence interval is always 95.
Yeah, depending on the model we are using. The model uses 95. That one, it is automatic, so it's not by your selection. So the model uses 95 confidence interval. If I use 95 confidence interval, it means the remaining 5% is the significance, the rejection region. That's why we are using a significance value of 0.05.
Okay, thank you.
Okay. Any other question?
Hello, Seth.
Yes, please.
So is it possible that the will show significance, then the p-value or the CI will show otherwise?
The z value.
Yes. So
You are saying
the Z value, the P value, and the CI is it possible for them to tell different stories? One is showing significance, while the other is telling insignificance.
I've not really seen something like that before, but I cannot say it's not,
Like,
but I don't know. All the models I've run and what I've learned, maybe sometimes the Z value can be closer to 2. It shows that you're having
mm,
significance, but it's not that strong. You can see from, and always you see from the both side. You can check the inflation. You see, the inflation is 2.12. It means it's very close to 2. And if you check the corresponding p-value, it is 0.03, which is also close to 0.05, which is the significance level.
mm,
And you can realize, you can also see from the confidence interval that the difference is too narrow, moving from
mm.
the confidence interval 0.005 to 0.002. It's not that wide. So it always goes hand in hand. It shows the
Okay,
robustness of your decision. It shows the robustness of your decision.
okay, thank you.
Yes. Please, any other question? Okay, so let's try to interpret the. Okay, so let's interpret the coefficient, which is important. CO2 is having a coefficient of 0.25, 0.25. The CO2 is showing 0.25 coefficient. We have learned in our previous lectures about dependent variable and then independent variable and the role each plays. We said the dependent variable reacts to the changes in the independent variable. If the independent variable changes, the dependent variable will react or will respond to the changes in the independent variable. So that change, is it significant or not? That's what the p-value, the z-value, and then the confidence interval is used to determine. And then the GDP, in this study, the GDP is our dependent variable. So CO2 is showing a coefficient of 0.25. In percentage-wise, it is 25.49% or 25.48%. It means that if there is a unit change, there is a unit change in CO2, if there's a unit change or a single change in CO2, it will cause approximately 25% change in GDP. That's the meaning of the coefficient. PM 2.5 shows negative 37, sorry, negative 0.37, which is negative 37%. It means that a single change in air quality or a single unit or a unit change in air quality level will cause 37% decline because it is negative, will cause 37% decline in GDP. So if PM 2.5 increases by a unit or increase by a unit, it will cause 37% decline or reduction in the country's GDP. Nitrous oxide is showing 0.059, which is 5.9%, approximately 6%, and it is positive, it means that a unit increase in agricultural intensification or nitrous oxide, it will cause a positive change or an increase in GDP of 6%, or it will cause a 6% increase in GDP. Someone should interpret the exchange rate for us. In the subsequent models, I will not interpret. I think our time is even almost up. Someone should interpret the health for us, the coefficient of the health.
Hello, I want to help. I want to try.
Yes, please, you can.
Okay, so if there's a single or a unique change in health, it will cause a 3% decline in the country's GDP. Thank you.
Please repeat. Please repeat what you said.
If
Your
okay,
network is breaking. I'm
if
not
there's a
okay.
unit or a single change,
Okay.
please, is it okay?
Yes, please.
If there's a unit or a single change in health or in people's health, it will cause 3% decline in the country's GDP.
Okay.
Thank
Okay.
you.
Great. That is true. So the health is a indicator for health expenditure. So it's like government expenditure. So it's like it's having a negative relationship. So the more government spend on health, it causes a decline in the country's total GDP. So as Anne said, that's it. But you can realize that it is not significant. It is not significant. This relationship is not significant. So if it is not significant, then you cannot make decisions based on it. If it is not significant, you cannot use it to make decision. Someone should interpret the exchange rate. Please, or you to try something. Try. If you have not interpreted a model like this before, this is the platform for you to learn it. And if you understand this, every model you run, this is the structure it follows. Any model you run, this is the structure the result follows. So if you are able to understand this, there's no model that you cannot interpret. There's no model that you cannot interpret. So try to explain one. I will not call anybody, but volunteer and interpret the exchange rate.
Okay, said. So for exchange rate, a unit change in exchange rate will cause a 0.256 decline in GDP, but it is not significant.
Perfect. Okay, someone should also interpret the money. The money.
Okay, so a unit change in the money will cause 0.3% increase in GDP.
Okay, great. So the same thing applies to the inflation. That one too is 0.2% or 0.3, approximately 0.3% decline in GDP. So that's how we interpret the result. I think our time is almost up. Let me run the other model. So that's the
Said, you have skipped the constant.
the constant, forget him, eh? Don't mind
Okay.
don't mind him. It does not influences the decision. It does not influences the model. It accounts for a lot other things which we are not much interested in it. So the main thing you have to check is your within R square and the overall R square to And this one is acceptable. 59, 69, 79, 80 is acceptable. If it is below 10, then you have to improve your model. Then if these are significant, your model chi-square is significant because you will report these things. You will not report the R-square. You will not report it. And a constant too, you will not report it. Terry, I hope you understand.
Yes, I understand. Thank
So
you.
you will not report the constants in your manuscript. Just pick the
Okay.
coefficient and then the significant value and then the R square and then present it. That's fine.
Okay.
They all have econometrical implications, but we are not into those technicalities here. So I will not go there for now. Maybe when we get there, we can explore what it really means. Then let's run the FE. So you see that I added RE here. So you will just change the RE to FE. So you change the RE at the end to FE. So the RE is the random effect. It's and then the FE is the fixed effect model. The fixed effect model and then the RE, they are the basic panel model. The RE account for unobserved heterogeneity. There are some differences in the countries which we did not account for. That's what we call the unobserved. We are not observing. There are some differences like culture, location of the country, placement of the country on the map, the country's management styles. Those things, we did not include it in the model. We did not include it in the model. So if you think those things, you want to account for it. If you want to account for those unobserved differences or unobserved heterogeneity, then you use the random effect. So the random effect accounts for unobserved heterogeneity. When I say unobserved heterogeneity, it means the differences in the countries that we are not accounting for. It can be their culture, the country's culture, the country's location, the country's management, business management, their governance structures, and all other things that we did not account for. Then you use the random effect. But the other way around, then you use the fixed effect. The other way around, you use the fixed effect. That one, it treats them as the same thing. But most, as I said, we use the Horstman test to determine which one to use. But in this, based on our cross-sectional dependency and then the other results, it is not appropriate to use them because it does not address the cross-sectional dependency. So let me run the FE. So you see that this is the FE, fixed effect regression, fixed effect regression, fixed effect regression. We have an R square of 62%, which is also okay, So you can see that this one, two, we're having these three highly significant. The same thing here, we're having this one highly significant. You can see that for the fixed effect, health is now significant. Health is significant, but I think here too, health was significant. So I think the result, okay, I'm comparing different. Okay, so you see this one, the random effect, the health was not significant. Yes, the health was not significant. But for the fixed effect, the health is significant. The health is significant. So I think for the fixed effect, money and exchange rates are insignificant. The same thing applies to, okay, so here, money, exchange rate, and health are insignificant. So it have a similar result, but it does not mean they are the same. They are not the same. But so if you want to use a basic model, you can use the Husman test to determine, or you can use one as your main model and then use the other as your robustness model. So I will not, our time is up. I will not interpret this because, as I said, it follows the same procedure as the random effects model. So you can see that the fixed effect model also follows the same process. It follows the same process. So let me see if I have one other model. Okay, so the mean group. The mean group, mostly, I don't like running them like this in STATA. You can use eView to run them, or you can use R or maybe Python. STATA, you can use the inbuilt command. But let's run them here and see, because I don't know, mostly when I run them, I get insignificance. So this is the mean group estimator. This mean group estimator. You can see that the variables are all insignificance. The variables are all insignificance. So this is the mean group estimator, Pesseran and Smith mean group estimator. It is showing that the variables, that's why I don't run these models in STATA using code. Let me run the, so the common correlated effect model, the one I said is suitable for based on our results. You can run them. It have the XTCCE. So the mean group is the XTMG. Then you select all your variables. Then you can run the common correlated effect. So the common correlated, it accounts for the cross-sectional dependency, which is the differences in the variable. So you can see that it's only health, which is significant, the health moderator, which is significant. I'll show you another ways to run them, and we will see if there will be a change in the results. So the mean group CCE, this one too is common correlated effect estimator. So these are all the models I'm running. It goes with the same interpretation. It goes with the same interpretation as this one. Just that this one is accounting it accounts for the cross-sectional nature of the variables. This one is what? This one is common correlated effect mean group estimator. That one too is here. Let's run the Discord-Cray model and see. Our time is up. Let's wrap up and close. So the Discord-Cray, let me remove the lag from it. The Discord-Cray, yes. So you can see that the Discord-Cray, we have the fixed effect and then the random effect. So this one have FE. So FE, you can see that this one is showing us a better result, or yes. So you can see our main variables being significant. And our moderators, only the nitrous oxide and health are significant. Only the nitrous oxide and the health are significant. And then let's run this called create RE. So all these are models. All that I'm running are different models, and they all comes with different results. And we have a point at which you have to use both. So as I said, based on our results, you can use this called Cray for your main estimate. And then you use maybe the FE and then the RE for your robustness. And then we have the panel corrected standard error. It also accounts for cross-sectional and heteroscedasticity. So you can run the panel Okay, so I think this one too is good. So this is what we will do. We will use the score create for our main model. Then we use the panel corrected and then the random and then the fixed effects for our robustness. So let me summarize the results. I think our time is up. So in our next lecture, we will do the heterogeneous analysis, causality test, time effect models, and then the lag model for the robustness. So this is the main models that you can use. We will share the codes for you to know. So that's the code for the common corrected effects, mean group estimation, and then the panel corrected standard error. You can also use the statistic here. You can use some of the commands here. If you don't want to use the codes, you can come here. We are dealing with panel data. And in the panel data, you have linear regression, binary. We are not dealing with binary. Sensor. These are all models. Dynamic panel. So this is GMM models. We will get there. We are not there yet. Then we have DID models. We have endogenous covariate sample, frontier, co-integrated data. Unit root is here. You can test your unit root without using codes. So let's see if we will have a model to run. So random effect. So let's select our dependent variable, which is, so this is how you can run it without using codes. So if you are allergic to codes, you can follow this process. Inflation. Okay, there's no offset variable. Let me check. So country ID, then year. Okay. Okay, so let's run it and see. So this is the random effect. You can see, let me suppress the constant term. So you can see that this is the random effect. This is not using codes. This is running it directly from the STATA command, but mostly it is appropriate to use the codes. There are a lot of packages here that you can try it. Let me see if I can get one code for us to, one model that we can run. Then we bring the session to an end. Okay, GLM models. Now we are not working with that today. Okay, these are all the ARIMA, GACH, AMA, threshold regression. We will get there. We will do all of them if time permits. Okay, so the longitudinal. Linear models, random, binary, GEE models, frontier model, GL. Okay, so this is the panel corrected error, the one we just ran. I think it's here. So if you don't want to use the code, then you can come here and use it. Let me run it and see. Okay, so the panel corrected standard error, you select your dependent variable. Those who are allergic to codes, you can try this one. So GDP, CO2, PM 2.5, nitrous oxide, health, money, and then inflation. So you can play with these things. You have the panel specific AR autocorrelation of residuals based on Debye-Watson, single lag OLS, weight panel, each of them. You can use any of them, but it should have a theoretical meaning. Okay, let me run it. Okay, so you see that I've run it. We are having a good result here. So this one, I didn't use any code. I just ran it from the STATA. So there are a lot of models here which you don't need codes. Please, if you have a question, you can ask. Then we bring our session to an end. So tomorrow we will finish with the we will extract this result into our result. Then we continue with the heterogeneous and then the robustness results, causality. Then we end with the data analysis on this. Then we take the models one by one. Any question?
Okay. Hello, Seth.
Yes, please.
Okay, so the models that we've run in Theta, if we go and run them in R or Python, are we going to get the same results?
It's unlikely. It's unlikely. It's not even you if you can check that the random effect. Look at the random effect that I ran from the tool using the interface or the inbuilt package. If you check the result where you see that it is different from the result I had using the command. Can you see that? You see, this is
Yes, sir.
random coefficient. Look at the significance level, the p-values. And look
Okay.
at the random effect we have earlier. The random effect we had earlier. Where is that one? You see this one. This one too is a random effect.
Mm,
You see?
okay.
So it depends on the software and the package it was built on. That's why you have to disclose in your report that maybe a STATA was used. STATA, even the STATA, you have to state the version of STATA that you used. That's why I say, you see, this model, the reason why I didn't do much on this model, the CCE, you see, I'm having a lot of insignificance here. But I will go and run the same model in A-views and I'll get significant. Sometimes there's a changes in the packages and the tuning of the model. So all those tuning should be the same before you get the same results. So you can run it in R, the same model, you run it in R, and maybe you get a different result from when you run in STATA or eView, because maybe there are some slight changes in the packages and the tuning and the settings. So you can see that when I come to statistics, and then I use this one, you see the random coefficient. You see there are a lot of things to tune here. We have the offset variable, suppress constant term. Even when you come here, we have a lot of things to do. When you come to the SC, we have the conventional bootstrap, jackknife, even the reporting, we have the confidence level to be 95. So someone asked if the confidence level can be changed. If you are using the package, the interface, you can make changes to the confidence interval. But you see that the code that we use has already set it to 95%. So all these things makes the result to vary. So the one you are using, you have to disclose it in your study so that if someone wants to replicate it, it will adopt the same method, same process, same software that you used in order to get the same results. So mostly when you run different results, different models in different softwares, you can get different results. Even the same software with different versions, you can get different results. So you have to state the software you used and the version of software you used. And even if you have different packages, state the package that you used. Please, is that okay?
Thank you.
Okay, thank you. Any other question?